So as I said, welcome to everybody. I'm David Rios, and I will be one of the teachers in this course. It will be mostly done by people from ISEMAT, but from other people from the what is called the AIHUB connection, and at several institutes at the CSIC. So I must. Okay, so basically, as motivations, we are finishing this year the lab, the etc. At ISEMAT, and therefore we wanted to leave some kind of legacy, and partly was this these kind of lectures that somehow summarize what we've been doing over these years. Also, through the AIHUB connection at CSIC, we've undertaken lots of interdisciplinary discussions between various groups, and we realized at the connection that there was some kind of need to support this kind of type of training. Also, we got this through consulting for other CSIC institutes, which we are undertaking. The CSIC is doing some statistical courses, but I think they are kind of oldie, and well, that was an opportunity to modernize this. And also within ISEMAT and some of our sponsors, we had the need of undertaking these courses. So basically, these are all the motivations for us to doing this. And I hope you'll have fun. We'll have fun. We all have fun, and maybe that's the opportunity to undertake various collaborations. Okay, so the description is like that. Basically, we're going to make a brief introduction to what is machine learning. Partly, most of the core idea would be to destroy some myths and somehow break some barriers that some people find about it. It won't be because it's an introduction course, it won't be a super in-depth course. So basically we'll go through the main trends in machine learning, so that people have idea of the core techniques and find out what is of use to you. So the idea is that we try to build here algorithms that in a somehow automated manner learn to perform some task of interest in science, engineering, business, or whatever. Most of the algorithms have a statistical basis, or maybe initially, and we shall see some examples, maybe initially some of the algorithms didn't have a statistical basis, but with the time, people have found some kind of a statistical basis. And the sort of core example would be support vector machines, which initially started through some kind of geometrical idea, but then some people find some. But most of them, as I said, have some statistical basis. And based on the data and expert opinion, which is useful, we make forecasts and support decisions. As I said, we'll go through several applications, at least one important application in science or engineering per chapter or per lesson. The idea is that to help people lose fear. It's something like everything you wanted to know about machine learning, and you never dare to ask. So that's the kind of thing, and go through several implementations in relevant problems. We shall focus on R. Typically, you will have two choices. At least this year, you will have probably in 2 years, the choices will be different because this changes a lot every year. But typically, you would have two choices, R and Python. So the sort of scripts and programs that we shall see will be in R. But if you prefer Python, we have in the room plenty of people, and I'm sure that if you want to ask questions about Python in relation with this, we'll be happy to answer them. So the objectives will be to present the core methods through 3 major paradigms. There's others which are more recent, but the major paradigms are supervised, non-supervised, and reinforced. We shall show some complex machine learning projects, real and realistic, so that you understand the richness and the possibilities. We'll talk. This is a sort of very fastly evolving field. I don't know. Every month there's some. I mean, this is the month of ChatGPT, but 1 month ago it was the diffusion models, etc., etc., etc. So that's very fast developing. So somehow we'll present the core, the basis, so that you can follow those, and we'll tell you where to follow the latest developments and illustrate some implementations. Anyway, I mean, just make questions whenever you want. That's it. So the first thing is, I mentioned before statistics. I'm a statistician by training. I'm a pretty old guy, and probably if we had put introduction to statistics or statistics blah blah blah, nobody would have joined the course. And it happened that we had like 200 people trying to join this course, probably because we just put machine learning. So there's tons of sentences like this, and probably a case that we have learned with the years. Basically, when you ask for money, you must say right now that you are doing artificial intelligence. When you are hiring postdocs who want to do a cool thing, you must say that you are doing machine learning. But in the end, quite frequently you end up old-fashioned logistic regression. That's what you implement, and it's been the case that we've done this. Actually, both terms are not that different. I mean, we tend to have some kind of hybrid approach. Actually, in the 90s, the concept of statistical learning was introduced, and somehow we can say that machine learning is some kind of glorified statistics. And one term that we like a lot is this computer age statistical inference. But machine learning is more trendy, I would say. But I mean, from a technical point of view, probably that's the right thing to say. And that's that's the title of a book, which I shall mention before afterwards, which is quite nice. Okay, Jose, don't worry. So what is true is that in the beginning, both fields have studied in different communities. So let's say that machine learning was more statistics done by the computer science community, and statistics was done by the mathematical community, let's say. And the jargon, as a consequence, is different, or slightly different, though there's a convergence. So as before, machine learners, computer scientists wouldn't go to statistical conference, and statisticians wouldn't go to machine learning conference, but now they are clearly converging. So you see, we for example, we are doing a conference in May, which is called Bayesian Inference in Stochastic Processes. And I would say that, I mean, when we started this series like 20 years ago, it was boring statisticians, but now I would say that 60 or 70% of the papers come from the machine learning community. Anyway, these are words that are said in the, like, I don't know, in statistics, they say, or we say, estimation in machine learning is learning, regression is supervised learning with continuous response, response is label, regressor is feature, etc., etc., etc. But basically, essentially it's the same thing. So some differences. That's actually a kind of important. In machine learning, the emphasis is on prediction. So you want to predict some quantity based on some other, and that's the emphasis. Whereas in statistics, in traditional statistics, the emphasis is on inference. So the typical problems of point estimation, intervals estimation, and especially hypothesis testing. That would be the in stats. There's a huge emphasis in quantifying uncertainty, and Carlos now is discussing these kind of problems because he was basically doing prediction, but now he wants to quantify uncertainty in his predictions. Whereas in machine learning, as we shall see, the emphasis is in optimizing. So in statistics, there's more emphasis on understanding underlying principles, and basically this is due because I don't know. Think of people doing biology, medicine, material sciences, etc., that want to understand the underlying principles, but the emphasis in machine learning is more on predicting accurately. So here is more interpreting, etc. Here is more on predicting. So I said the duality, maths, computer science, and more human intervention and machine intervention. So these debates between machine learning and statistics has been reflected in tons of papers and by sort of super famous people. I put here a few of them, and it's of course we don't have to time, but if you have just time to read one, I would suggest this by David Danson, which is the title is quite meaningful: Statistics in the Big Data Era: Failures of the Machine. But some of them are super classic and well known. Okay, so in machine learning, I mean, a definition from a sort of a book, a huge book, which is quite meaningful at the moment, is a computer. We say that a computer program learns from experience with respect to task T and performance measure P. If its behavior with respect to that task measure according to P improves with experience C. If you replace a computer program by a statistician using a program 20 years ago, that would be again statistics. That's what we used to do, right? And what we used to do. And one thing that we shall learn through the various lectures is that there is this emphasis in representing, evaluating, and optimizing, which will, as I said, it will appear in various sessions. Okay. The tasks. I mean, we'll see most of these, but classification is of interest in many scientific and engineering fields, possibly with missing entries. Regression, in which we, based on a few variables, we try to predict some variables of interest, and that will be, I mean, when we go through, we'll go through classical regression because we need to go through it, but when we go through neural networks and deep neural networks, that would be automatic translation is also an important machine learning task. Anomaly detection, synthesis and sampling, which from the standard names in statistics would be density estimation and sampling from that density estimation, density estimate, visualization, compression, etc., etc., etc. And here I put applications which have been, mark the path. For example, well, the first ones, content filters and recommender systems are very old, and probably the start of the field of machine learning. But here are super cool things that people are doing. Some of them we are working on that. For example, in cancer screening and drug discovery, there's people working on that at ISMAT, and these are like the sort of popular things in the last few months, as I mentioned, natural language processing, image, video, and conversation generation. This has been on the news in the last weeks. AlphaFold 2 in particular was yesterday on the news because of the BBVA prize. And AlphaFold is, for example, creating a revolution in the area of drug discovery. And so all these tasks are on one hand allowing to do things that scientists and engineers used to do in a much more efficient way. And one nice example would be drug discovery. Years ago, it took years and lots of euros to develop a drug if you were successful in the end of the pipeline, and now it's much faster through these things. And so there's examples of things that we do now much more efficiently, and things that or technologies that it was just a dream like 10, 15 years, well, 20 years ago, now are starting to become a reality. And that's another example. That's one prime example would be autonomous driving systems, automated autonomous vehicles. And again, that's an area in which ISMAT has been working, and other institutes at CSIC. So this is super sexy, super cool, but there's some buts, and we'll go through those buts in the last days. There's issues like privacy, safety and security, and that's quite important for the research, our research, equity and bias, and some which is becoming quite important is explainability and interpretability. That's so somehow going back to the debate that we had between statistics and machine learning before. In many areas, and we had one discussion with some colleagues from archaeology yesterday. In many areas, the scientists need to interpret the results, and many of the models are not easily interpretable. We'll see in a recurrent manner a figure of some kind of hierarchy of machine learning algorithms. We'll see that quite repeatedly. So that's quite important, and that's quite important. That's becoming quite important. Because of, to see the importance of these technologies because of a couple of laws. One is the GDPR, which in some areas requires for some decisions require interpretable and explainable or explainable algorithms. So that's sort of pushing the research in these areas in machine learning. And the other one is, the other piece of law is the European Union Artificial Intelligence Act, which is currently being discussed. And what this law will promote is a lot of emphasis on the security and safety of machine learning. So therefore, it's a good time to undertake research in this area. Okay, so there's hundreds of cartoons like this, right? And I picked one of them. So yeah, there's this other guy which is entering into the picture. So basically, as I said, machine learning somehow is like a well-dressed statistics, right? And artificial intelligence is well-dressed and well-presented or well-sold statistics. So as I said, and probably this course is one example of this. Should we, had we presented this like this, only Simon, Pablo, maybe Carlos might come to the but Unai wouldn't come, right? But well, in such a way we have get a larger crowd, which is good to create synergies between researchers. Okay, so it's also interesting to, sometimes I get nervous because everybody talks right now about artificial intelligence, and well, I say, well, actually you are not doing, it's not just artificial intelligence, but blah, blah, blah. So it's nice to have this sort of historical picture, and also to understand that this has gone through waves, through several ups and downs. So in the 50s, mid-50s, though Turing had some mentions before, the term artificial intelligence was coined, and there was lots of excitement. We'll do so super cool things, right? But the kind of projects was that were studied for example, the Hanoi Towers, right, which is depicted this. So there was a decrease in the financing of this kind of research because of a number of well, other things became cool, and there were some kind of negative results that we shall see in like 4 or 5 days, and that put a sort of stop on neural network models at those times. But then again, there was a new wave of interest in machine learning and neural networks, which is around the 80s, 90s, and the typical example I'm putting here, anti-spam tools. So again, there was a sort of boom, and that was when I started my work. But then again, other models became cool, and there were some technical problems that were not mathematical problems that were not solved or were not properly solved. So there was again a decay, and then in the last decade, there was a boom of deep learning and all the fashion, and that was due mainly because of this computer vision successes that there was in those years. And so we are now in a boom, and my feeling is that the boom will be on the top for many years now. So to sort of put up, artificial intelligence is more than machine learning, right? So things like knowledge bases, etc. Knowledge bases were more ontologies, and all these kind of things are also part of artificial intelligence, and yeah, I don't know, decision support, multi-agents, etc. And then there is machine learning, representation learning, and deep learning. So we'll go through. I mean, we'll move in this space, but we'll need to cover old stuff. I mean, old stuff like logistic regression. So we'll move in this space. By the way, if it's interesting to check in this law that I mentioned before, the European Union Artificial Intelligence Act, the Appendix 1 defines what European Union legislators think about artificial intelligence, the type of systems that are based on AI, and certainly they include machine learning. There's three core topics. One of them is machine learning, but it's interesting to see that they mention also statistical, Bayesian, etc. methods. Okay, so that's what we plan to cover, unless you have other things or suggestions. So we'll start with a broad overview to have a broad sight of the whole landscape of machine learning. And then we go through a sort of logical path starting with regression algorithms. I mean, going in some depth through regression algorithms. So this means algorithms for, I mean, supervised with continuous response. Then we'll go through classification, let's call it advanced classification algorithms. Then we go through a class of algorithms which refer to trees and forests, which can be used for both for regression and classification. And next we'll see support vector machines and probabilistic graphical models. By the way, that's a link with what we do after this class, which is on causal models. And then we'll spend quite a bit of time on, let's say, the responsible of the current boom, which are neural nets and in particular deep neural nets. So we'll spend some time on that. Then we'll move to non-supervised learning. So this means that we won't have the Y's and we just have the X's, and we need to do things like density estimation, etc. We'll spend some time on reinforcement learning, which basically means that the system learns online as it sees examples, makes decisions, and receives a reward, a positive or a negative reward. Particularly, one thing that we'll sometimes discuss is about, let's say, general purpose algorithms or general purpose artificial intelligence. I personally think that that's a sort of the promising way, the promising path to this general purpose will be reinforcement learning and specifically what we call multi-agent reinforcement learning. And some people from Barcelona will from the institutes in Barcelona will tell about it. And finally, as I mentioned, we do this, which is super cool, etc. But we need to know a little bit on ethics and security of this. That's kind of important. So I should, I mean, most of the the predominant paradigm, I would say, it's based on maximum likelihood estimation plus a regularizer. So that would be the emphasis, but we will make sometimes mentions on Bayesian approaches, and that's because Simon is a Bayesian, right? But actually, let's be honest. So this is the predominant paradigm right now, and there's when we go through Bayes, we still find some difficult problems, computational problems that still need to be solved. So on one hand, this is quite stimulating from the point of research, from the research point of view. And actually, we'll try to cover these problems in the follow-up course, which will be on Bayesian data science. So, I mean, at least our part of ICMAT is not just Simon, but most of us are Bayesian. So that's why we want to. So the course will be based on R, and we'll use a lot Keras, which is there's various libraries, but we'll emphasize Keras. Most of the stuff, part of the stuff we can do it. We will be doing it on PCs and laptops, etc. Some of the stuff we won't be able to do it on PCs, etc. And luckily, Alfonso, which is one of our IT guys, is doing the course. So I hope we can convince him so that they give us access to our machines. But actually, the CSIC has pretty good installations, HPC installations, and that's an opportunity to know them. So we probably do some kind of virtual tour through those machines. So the slides in English, the labs will be in Spanish, and we'll make some kind of dictionary. And well, we'll use images in the slides from here and there from the bibliography. I mean, you go through the books. you'll recognize them, and that's our acknowledgement of those images. That's a few books relevant that will follow of various emphasis. For example, that's these are sort of, I mean, probably this is one of the founding books in the area, and that's a sort of simpler or introduction version to it, right? A more like a sort of broad view of a combine of machine learning and statistics from the old times to the modern times, and it's very easy to read, and I love this book, right? A bit boring, but a more in-depth of the area of deep learning is this basic book, and reinforcement learning is there. And some other, Bishop is also very interesting. There's a collection now, relatively recent, of books by a publisher called Manning, and they are quite good. They tend to be not very mathematical and more verbal and more computer-based and computer exercises, so they are kind of useful if you, but I mean, they are like quite focused, I don't know, for example, in natural language processing. So if you are interested in natural language processing and more from a computational point of view, that these are good. And we'll put a few papers, sort of meaningful papers, if you want to read them, or if you want to keep them, right? Okay. Well, this is good for deep learning with R. And so these are the logistics. So we'll do on Fridays from 10:15 to 11:45 in the peninsula, because we had some colleagues in the Canary Islands. So hello to Polo if he's there, right? So the sort of structure that we want to follow is basically not today, because today is the first day, but we'll try to reply. I mean, if there's questions through the week, we'll start by replying the questions. Then we go through some concepts through the slides. Then we'll go kind of oversee some of the labs that we do, and I mean, of course, we won't have time to go through the labs, but we'll explain the core ideas, and then if you have time and if you want, you practice them. At the end of each chapter 1, 2, etc., we'll do some case study that some of us have been involved. For example, the first one will be delivered by Simon on COVID research, COVID-related research with regression and classification problems. And then if somebody wants to propose problems, etc., well, we are more than happy to discuss them. If somebody wants to send questions that we discuss the first thing in the class, in next class, just use this one, and typically we'll answer in the next section. So don't expect lots of interaction, because we have the course list is this one, and basically we'll use it to remember. Well, next Friday we are meeting, etc., etc., etc. So this will be the course Zoom, and slides, stuff, data sets, and links to the sessions that we are recording will be available through this GitHub or this website. Okay, and that's the sort of organization. Any questions or comments? Or, of course, if you want to send me an email, just do it and I'll try to respond. Okay, now I have to do the trick. I do have to stop this, or no, probably not. So we're gonna stop for like change the slides. Yeah. In the meantime, if you want to make a question or I'm sorry, I forgot. No, I should go back to this one right here. So just how do I show it again? I need to show. Okay, so with each session, we'll have one or more labs, right? And let me just go through one, two, so that you understand the mechanics. So basically, at the lab, we'll put the our markdown documents for this particular lab. We will put the word generated by the RMD thing and the RMD thing. But I mean, once you know, I mean, you can generate your own words if you want. I mean, if you want to do it. So basically, we'll go through. We'll provide these kind of things which try to explain what we are doing. In this case, basically, we've said hello in the. So basically, this is a hello lab in which we introduce what is R for those who do not know how to use it. And typically, we introduce some text. And we recommend some places where you can learn a little bit of R. Where you can learn a little bit of Markdown and how to install, etc. So we recommend that you install RStudio. That's like will be much easier. And then we explain a little bit of R. I don't know if I can make a check here in this room. All of you know how to use R? Okay. So I mean, the basic idea is you follow these sheets, right? And then if you have questions, you ask us, right? Okay. So it's a super powerful calculator, R, right? And with a slant towards statistical computing, right? That's just think of it. And here we explain. I mean, one thing which is important is that it uses a vectorial representation. So X would be a vector, right? And you can operate in a vectorial manner. So 2X is a vector, which, so one example would be, so one example would be like above. I'm filling the X, right? It's being filled by 10 uniform random numbers. R is for random number, unif is for uniform. And the parameters are 10. I'm putting 10 numbers, and the uniform is between 6 and 9, right? That's an example. And so X is a vector. And then you can see that we can operate in a vectorial manner. So 2x is the vector, which is double the log x is the logs. And I can multiply vector x by vector I in such a manner, etc., etc. So that's a sort of, I would say, is the core concept or the core difference to other languages or sort of more standard things. And then, so you have all the mathematical operations, and then you have lots of commands and commands for statistical purposes and packages developed by the community for statistical purposes. Basically, anything interesting that you could dream of has been probably programmed in R and is available there, right? And if not, it's because it's a super edge. I mean, last frontier research, and somebody, and therefore somebody's programming. I would say that Simon and Chema will discuss this. As I said, there's an alternative which is using Python, but I would say that R is stronger, still stronger because it's been for more years as a statistical tool, a support tool, than Python. But Python is catching up. Okay, so so then what we show is some, in this particular example, we show a little things to remember. I mean, to sort of get you familiarized with R and statistical. So things like, how do you do a histogram? So you just have a command which is hist_x, right? I don't know, quantiles, etc., etc. So basically, the idea is you just go. It's been. I mean, we've gone through this like 3 or 4 times at least, and practice, etc., and tried with. Well, I tried it with Pablo as a cobaya, and yeah. So we've tested them, right? So it's kind of easy to follow. I now will show you how to launch it and run it, etc. So that this is basically, you read this and then you practice. I don't know. We show things like other distributions. A little bit of models. That's an important thing, a kind of important thing. We'll use models, right? Lots of models. And the command or the syntax is some kind referring to some command referring to a model. In this case, it's a linear model, a regression model. And it's always of this type. You are trying to explain or predict some variable. In this case would be y, in terms of a bunch of variables which appear here. In this case, you're trying to predict y as a linear function of x. So that would be the model you're trying to estimate. Right? You're trying to estimate a and b, right? Yeah. So as I said, we're going to use many packages in R. That's one of the strengths. And the thing is, so you have packages for virtually everything that you need. The simplest way to do it is through a command. I shall show you in a minute. Through RStudio, you go to the command tools, install packages, and then you'll see that you can get. So here I'm explaining how do we use something called utools. The next thing, which is until now we've been generating data, but I mean, of course, you need to upload or read data from your experiments that you have in some file or files or somewhere, right? So the sort of easiest way is to go through some commands provided by R, which say session, set working directory, to source file location, and you'll have there the data that you want to do. So in this case, for example, we put you at in the GitHub. We have put you as to play a data set called data0.txt, and if you do, you get it and upload, and then you make all these kind of things, right? This is sometimes some libraries or some packages are already available with the basic version of R, and MASS is one of the examples, right? So you load it with library, and then you do these kind of things. Okay, and well, some other examples with data. This is a sort of introduction. It's super powerful for graphs, right? And that's an introduction to some little example for graphs. And by the way, one powerful thing of this is that this is done with R Markdown, right? So one powerful that would be a perfectly a tool to prepare a report, a scientific report or a paper. So that's quite powerful. This is done in Word, right? But you can do it in tech PDF, or you can do it in HTML. So HTML. So the kind of templates that we put, you can use them. You can edit, and we are putting this date and my name, etc. You can change it, etc. And you can play with them. Okay. So now I'm gonna. That's the sort of the spirit of the thing, and I'm gonna show you on RStudio. Any questions, or you can make it then? So in the it's not there. Well, in the GitHub you also have. I wrote you I showed you the word that I generated, but we have also the RMD. So basically. Okay, that's I click on the RMD, and you will, once you have installed RStudio, right? You have the instructions. Basically, it's divided between four screens, right? It's a development environment, interactive development environment, which is quite powerful. And basically, here you see the document, the Word document that I generated before. You will see it, and you can basically do Control Enter through the commands to see what's going on. Here you see the actual commands, and yeah, you basically see the commands. Here you display information, various types of, for example, the help thing, which is quite powerful. And above, it's saying also, it's showing the commands and some structures. So basically, you go to this part, and if you can see in the upper part, it says the head. So it says that was the title of the thing, who did it, the date, right? You can change all of this. And you can see some commands to mark the text. The text that we wrote and appear in the Word before. That's the kind of thing. So you must use marks to show or to mark websites, for example. So that's text in plain Spanish. And now here there is areas marked by these three things, right? And it says R, so it's a chunk of R. And that's how these are the commands that I put before, right? For example, if I do I do control and enter, right? And I do the next one. So here I'm displaying the, so I generated this, I generated 10 random numbers from a uniform distribution between 6 and 9. And then I want it to be displayed, displays, etc. So you do control, etc. And that's the mechanics. Okay, it's super easy. But if you have questions, just send. I mean, if you want, we can do a Zoom session. I mean, let's try and we can do a Zoom session, right? Okay. Yeah. What else? Yeah. So 2 important things. If I can, how do I move? Yeah. Yeah, a couple of important comments. One is the tools thing that allows you to install packages. That's quite important to know. So I do tools, and you can see that there is install packages. That's quite important or useful. We are connected to internet, and then here you start. And it will help you to find that's quite important. That's quite useful. The other thing which is, I cancel it. The other thing which is useful and important is, well, all of them are important, but the other which is the session, the set working directory in which you say where are your files, or the file that you want to source file location, because otherwise you need to do a scan, etc. There's various commands which are quite boring, right, and intimidating to learn, and you need to know the path, etc. So that's quite useful. And the third thing which is super useful and powerful is the help. I mean, you have a wonderful text course of statistics through. If you are curious enough to learn whatever, I mean, you learn lots of things. So, and like here, I put here loading, attaching, and listing packages. That's I asked for help at some point, right? Okay. So the mechanics, I think the sort of time-wise is that, and learning-wise also, is that you try with the and if I don't know if a sufficient number of people is having problems, just send me an email and we arrange a Zoom session and we go step by step, because I think it wouldn't be very efficient if right? Okay. Any comments or questions from here? Okay. So the basic idea is that that's the lab for session 0, which was basically a hello and logistics thing. At each session, at each lecture or each chapter, we'll have a bunch of labs to practice the concepts, right? Okay. So a good, if there's a question, menos cuarto, ¿no? 45. Sí, okay. So a good place to, so we start now with the proper, we've finished logistics, but a good point to start the chapter 1 is just reading this thing. So our idea with chapter 1 was to sort of provide a broad overview of what we are going to see. And the idea is that you get a feeling of the core topics. I mean, let's call it all of the transversal topics, all of the topics which are transversal to all machine learning things, to find out what are the core problems and some of the sort of traditional methodologies, right? So we are gonna the labs here provide a sketch. Basically, we go very quickly through calling what is linear regression and the problem of overfitting. That's a sort of major problem in statistics and in machine learning. One thing that we shall be discussing is, okay, we recall what is linear regression, that most of you will know, but we make an emphasis on what happens with when the problem is large scale. So when we have lots of cases, a big N, or we have a big P, a big number of, or both things. So that's the sort of distinctive things. So we also discuss as a sort of transversal topic the problem of model selection. So what we have several potential models for a problem. Which one should we model? Or we have a model and it has several hyperparameters. How do we choose those parameters? In particular, we use a sort of well-known, which is KNS, nearest neighbors, and we make an illustration of logistic regression. So you can see that it's a sort of broad view of everything. Then that's supervised. So we explain what is non-supervised with some ideas from principal component analysis. And we explain, we give a sort of basic illustration and some ideas on projection and compression. And again, as I said before, is so well, we kind of know what is principal component analysis. Well, maybe some of you, but it doesn't matter. We know the sort of mathematical principles, but then we want to explain what happens when the problem is very large. That's a sort of continuous idea that will follow our discussion. And then as sort of transversal topics, we'll recall some ideas from optimization. If you remember from the first part, we said that there's an emphasis on optimization in the machine learning community, let's say. And this emphasis comes because they focus, we focus on maximum likelihood estimation. So we want to optimize the likelihood, right? Or either maximum likelihood or sometimes maximum likelihood plus something which is called a regularization term. We want to optimize something. So therefore, you need to have some idea of optimization. You don't need to become an expert, but if you want to do sort of new things, then it's better if you have. But typically, I don't know, R and Python, etc. I mean, when you invoke a model, a type of model, a neural net, etc., I mean, somebody has done it quite efficiently, etc. But I mean, I think it's quite important to know a bit of the ideas, right? So a bit of optimization and a bit of validation, right? That's another. So I would say as sort of transversal topics, model selection, optimization, and validation. I would say that's sort of the basic background for everything. I would say, and that's quite. Therefore, I think it's quite important to. I mean, we won't become a super expert in optimization, but we need to have some idea, right? Yeah. So that's basically what we want to do. Okay, so let's go to I look super old. I have never. It's pretty bad. Okay, so we start now, or we actually start. The idea of this topic is to, as I said, provide a general introduction, and in particular, this 1.1 is an introduction to supervised learning. So we're going to do both. So the idea is that between today and the next Friday, we would cover this chapter 1, including a case. Probably the most interesting is what Simon will say. Okay, so okay, it's not working now. Okay, yeah, it works now. So our broad overview, so supervised, unsupervised and reinforced learning, that's the sort of, so that you can start identifying what are the topics of interest for you, for your research and your applications. Key transversal concepts, training, testing and validating, etc. Key conceptual strategies, MLE, maximum likelihood estimation, MLE plus regularization. So that will be the core. Actually, that would be the core of this course. But we'll mention, because it's deep in our hearts, the Bayesian approach, right? And some key data analytic strategies. So that's the core. Okay. Sorry. So I've reviewed, I've taken this from Wikipedia. That's a definition of machine learning. I've put in boldface some stuff, so that was more interest. The first one we already said, but one thing is that it's closely related to a new term like that it appear, computational statistics, right? But not all ML is statistical learning. I should say that that's true, but there's a tendency that discovering a new machine learning, a new machine learning approach, and typically the type of work is then trying to make it statistical or provide a probabilistic base. And a prime example would be support vector machines, or things like TSNE that we shall see. Again, initially it has no statistical description, but now there's a statistical description of that. Mathematical optimization is quite important. That's why another term that data mining, that's kind of old. That was a sort of trendy topic, let's say 30 years ago, etc. But it's also related. It's mostly related with unsupervised learning, and also in business applications. We used to talk about operations research like I don't know, 30, 40 years ago, but now people talk more about analytics, predictive analytics, etc. So the business applications tend to be called predictive analytics. So, but it's the same guys basically with a different hat, Yeah. So the red part is these are some examples to sort of motivate, and the red part is quite important for. at least from our point of view, from our point of view of the people who are in this site. Maybe in biology, in medicine, well, in medicine actually this is, but maybe in some sort of other basic sciences, or in physics, in fundamental physics, the red part is not that important. But from our point of view of research and what we end up doing with, or what we hope that we end up in doing research, the red part is important. And I put you some examples showing that uncertainty is, well, it's almost ubiquitous in life, but in machine learning isn't. So I put you, I'm going to do like 3 examples. All of them are actually coming from examples that we've been working for sure. Somebody at the AIHUB connection has worked on that. But for example, given a certain transaction with a card, right? We would like to know. We want to forecast. The typical example is whether it is fraudulent or not. That's a typical classification problem. And that's fine if you want to do it, but we do it with some purpose, right? We do it to either stop it or not, right? So when you insert your card, I should stop it or not. If I suspect that it is fraudulent, that it is for a sufficiently important amount of money, and this client is sufficiently important, then probably I should stop. If not, probably I should not stop. I mean, if I stop it, I stop the losing money. But if I stop it wrongly, then my client could get angry, etc., etc. So we do this for. I mean, of course, there's the scientific. Orgasm, etc., etc. But we do this. I mean, from at least how we conceive this is because we do this for this kind of to supporting decisions, basically. I don't know. So, another example: a person with these Facebook likes that's from another project will buy this type of beer, right? What is the probability that a person with these likes will type likes in, I don't know, concerning football, concerning tobacco, concerning politics, blah, 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 will buy this type of beer? Of course, there's a plethora, and that's a complex problem, but I do it, we do it. Somebody asked us to do it because I want to send my brand, my beer brand, right, to make him buy it, make him or her buy it. Okay. And that's another example. A person with these tweets is he or she is doing tweeting, etc. Can I classify him or her as a conservative? Because I want to send him political messages to make him vote me or change his or her opinion, right? So the red part is because we do this, we do these predictive models to undertake some or support some decisions, which entail money, entail lives, entail impact to the environment, etc., etc. Right? That's quite important, and that's something that we shall insist in this. We do this with a purpose. As I said, I mean, part of the purpose might be your scientific satisfaction, etc. But in the end, I don't know. You have some biological, but in the end, somebody, or hopefully somebody, maybe not today, or maybe not but in a few years, somebody will use it to develop new medicines or whatever, right? Okay, so and I want to insist in this. So beyond something that we shall mention is, well, is the fit of the model good? Is it predicting accurately enough, etc., etc. Beyond this, we do this for. So I mentioned in fraud detection, typically we have a classification problem. So we have to detect whether some transaction some operation, whether it's fraudulent or not. So that's a typical classification problem. And we try to check whether the predictions are good with the, I mean, we would like to have false positive, few false positives and few false negatives. And we'll see that the tons of accuracy measures revolve about various combinations of those kind of things. Beyond this, so we want to do well in this, but actually what really matters is whether are we minimizing the monetary losses, right? So that's pretty good, but that's what it cares for us. And it's the same. It's the same in many examples. Like I don't know. We did this aviation safety risk management for the Spanish government. Okay, we did this super nice, huge forecasting models for accidents and incidents, but and the impacts. But really, what the guys wanted to do is we don't want airplanes in Spain crashing, etc., right? So that's super good. Okay, that's the sort of end. It's the red part again. So machine learning, and that will be a sort of a permanent discussion in our times of big data. And big data is a sort of old word already. So we'll have to deal with problems with a high volume of data, and so we shall talk from time to time about space scalability. So, right, we'll have to deal with a variety of types of data: text, images, sound, video. This has been quite popular in the last few weeks. It's appearing in the newspapers and the TV, etc. The velocity is quite important. So we have high frequency data, time series, dynamic models. Carlos is specialist on that. So we require, if the frequency is very high, as we are doing now with an anomaly detection problem, so we require some kind of time scalability. So I don't know, maybe, I mean, the idea is we want to forecast, we want to have a good forecast, and we need to forecast, but maybe we lose too much time in forecasting too much, too advanced, too long in ahead. So that's the kind of compromise that we need to study quite frequently. And that's the sort of, that's the red V, the red part that I mentioned before is that, okay, that's, all of this is a lot of fun, but what we want to create is actually, we want to create value by supporting decisions in the end. Okay? Or at least that's our point of view. That's so we've done through, we see this, that's a sort of a motto that will appear. This, remember, we will need to represent the problem somehow, and we see many examples depending on the models. We need to evaluate the kind of model that we use, and we need to optimize the performance measure that we choose. Okay, that's a sort of it will be repeated several times or many times over various chapters, models, etc., etc. Okay, so three core themes. Supervised learning, there's others, but supervised learning, in which both inputs and outputs are available. And the typical classification is between regression, when the outputs are continuous, and classification when the outputs are discrete. One example would be that some people are doing at CSIC is, for example, we try to detect whether some type of substance can be qualified as an active cannabinoid, because that's good, for example, for I mean, why? So that's a lot of fun trying to, because you have these molecules which have this very complex representation, and it's a lot of fun to try to forecast whether. But we do this because, I mean, or somebody does this because this will help to cure Alzheimer's disease, for example, right? Unsupervised learning outputs are not so here we have X and Y's. Here Y's are not available, or maybe the Y's are the X's, right? And the typical examples are density estimation. So we want to see how these features distribute over the another typical example would be clustering. So we want to find the groups of how these X's cluster. We want to detect outliers. So some odd X's, can we justify or can we provide some kind of explanation? And we want to visualize this. And one cool example was to try to determine that we did refers to determine what we call a singular community. So in a based on the likes that people do in Facebook, try to determine groups of users with similar likes, and therefore that's a target, a marketing target, for example, or a political marketing. So supervised, unsupervised, and reinforced learning, and basically that's we somehow find the responses online. So there's a system which has some access, makes some decision, and gets a reward, and based on that reward, we should optimize the behavior of such system, and the sort of mathematical framework, or the mathematical problem or the statistical problem would be the domain of Markov decision processes, more largely decision process, right? And again, at CSIC, one example, a cool example or cool application of this are autonomous driving systems. Again, it's super cool to do these models, forecast, build the decision processes, etc. But what we want at the end is that this car drives by itself and takes me to my home, right? Okay. So actually, there's other there's semi-supervised and some other flavors. Okay, but these are the three. Some actually, I would say most of the books just refer to these two, maybe these collaterally. And actually, there's books on this tend to be sort of monotopic, but I think it's quite important. I think this is a super promising area to study, and it has many applications. And I said somewhat blurry borders. This is a map from, I think it's Barber's book, and you can see how Barber views the world, and there's connections all over the place, etc. And something that a problem which is called lookalike modeling. So basically, for example, a marketing company gives us like 50 people, I don't know, or what the people that we are here, we are like 10 people with our features, but 10 is a company wants to send marketing information to 500, but we are the 10 real people. They would like to find like 490 people which are closest to us, so as to target that information. So this problem is called lookalike modeling, and it has Facebook has solutions, etc. That's a and that's a kind of you could actually view it as supervised and unsupervised. So it is, as I said, the frontiers are somewhat blurry. Okay, and to finish, because we have like just a KitKat moment, and I want to explain what this guy proposed, because that's the sort of prevalent paradigm in machine learning. That's maximum likelihood. This is Fisher. He's a genius, but now with this historical revisionism, for example, his plaques at the university and where he lived in London are being removed because he's a sort of scientific genius, but he promoted eugenics, etc. So what this guy promoted and what this guy promoted, and that's Thomas Bayes. So in a very simple example, I will go through and I like to show that this is actually, in this very simple, that is actually what we are going to do with more twists, more complication, more dimensions, blah, 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 but that's basically what we are going to do, and compare it with what we would like to do. And what essentially happens, in my opinion, is that what we would like to do, and Simon would like to do, cannot be done in many cases yet. So that's a sort of challenge to do interesting things. So and I think it's a nice time. So that's you can formulate in many examples in many ways, but we some of us likes cybersecurity a lot. So consider a protocol, cyber attack protocol, recovery, and we want to assess it. We want it. You could think of the protocol of from a snowfall from like Filomena. So Madrid has a protocol, and we want to evaluate whether it is good, is sufficiently good or not. Probably to compare it with another protocol, right? And it's a oversimplifying of this. So we have tested it in 12 cases, and it has been effective 9 times. This is not precise enough, but we must say that, for example, the system was up in less than 1 hour. So we have this attack, we apply this, and in 1 hour, I just remember that the cyber attack to CSIC, I don't know if you were aware, probably we are still recovering from it, etc. But okay, so the idea is we have this protocol. Is it good enough, or some other organization which is trying to sell another protocol to us? Is it better to move to that protocol or not? Basically, right? So that's a super simple problem. That's basically we want to try to estimate the probability that we recover or the proportion of times that we recover in sufficiently fast given this data. And that's a binomial experiment, right? So we are interested in the number of successes in n trials. We consider the success probability in one trial. We call it whatever we call, P or theta or whatever, or P from Pablo or C from Carlos or whatever. So we consider the distribution. We need to formulate a model, a probabilistic model. We formulate a probabilistic model which in this case is a binomial. And given the data, we formulate that would be the likelihood in this case. So, which is, there's another number, but we don't care. Basically, this is saying that we are successful 9 times and are not successful 3 times. We have some constraints, etc. I removed the number because a number here which I don't remember. Well, I do remember, but I don't care about it basically. Or what I want to do, or what we want to do. And basically, at implicitly or explicitly, sometimes implicitly means that when we write something in R, these commands, LM, Y, this little curly thing, X, etc., is basically implicitly defining something like this. And we don't care. Well, sometimes we don't care. Okay. So the likelihood would be this, and then typically for computational reasons, we will compute the log likelihood. which is here. So you can see that this is, well, this is not very difficult to optimize like this, but if I put like this, it's much easier. So again, I do these commands in R, etc., and basically what it will do, underline, it will be computing the log likelihood. And then we want to maximize, and that's what is called maximum likelihood estimation. We maximize this, or currently we maximize the log likelihood, right? And in this case, it's very easy. We compute the derivative, make it 0, and that's the estimate, which is surprising. I mean, all this boring stuff that I said, just basically to estimate this by the number of successes divided by the number of opportunities. Okay, this is the maximum likelihood, and that's basically in more complex forms what we're going to be doing, right? When we do, when we fit, in a few weeks we talk about fitting deep neural network. Basically, we are doing these kind of things, but the problem will be much more complicated. We'll need numerical processes, but that's what we do. This has a few defects. For example, if I don't know, if the number of successes is 0, we estimate with 0. If the number of successes is 12, we estimate this probability with 1, which is doesn't make. I don't know if our I don't know if the 3 papers that we submit get rejected. What is the probability that it will be 0? Which is, I mean, basically we would have to look for another job probably. Okay, and for future observations, for predictions, that's what we want to do. And actually, deep learning models will make predictions, right? So basically, we find this estimate, we plug in, and we make this kind of forecast, right? But it has a few defects, and that's why we use sometimes Bayes. We try to get we do Bayes. This has also the good thing from our point of view that it uses prior information. In many scientific contexts, you'll have prior information and you want to use it. In deep, this is a subject of debate. In deep models, with this huge amount of parameters, there is some debate on whether it's meaningful, but there's discussion about this. And there's let's say default priors for this, right? So either because of technical or because of scientifically meaningful, you have information. So you need to combine the information of this with the how do you call it? With the likelihood, right? Through Bayes formula, and then that's the posterior. You summarize it, and then you make your forecasts, your probabilistic forecast, and that's one of the strengths that you make probabilistic forecasts. That's something that we are discussing with Carlos at the moment, and that's one of the strengths. Okay. The problem is that, well, I said, this was very simple. This was a very simple example, maximum likelihood. But when you go to this huge, we know how to do it more or less efficiently, right? So that's why the predominant approach in machine learning is MLE. This is doable up to certain scales, but not so much in the sort of super huge machine learning models that people are dependent. And that's why we shall emphasize MLE plus regularization, and we'll explain in a minute. Well, next week what is regularization. Okay. So, any questions or comments? So you have the if you have questions through the mail, if you have time, I think it's try with the ER things, and if there's lots of doubts, we can arrange a Zoom session on Wednesday or Thursday before. I guess we can stop here.